classified the properties of ether. One as use base. Okay. In this use base, we have found that ethers react with strong mineral acids to form their corresponding mineral acids. This is some that is ethers are use base and reacts with strong mineral acids to form corresponding oxonium salts. Oxonium. Mineral acids and Lewis acids. Okay, this one we have done. Second, what did you do? Cleavage of carbon oxygen bonds. Okay? No. Not cleavage. Second thing we have done is that is not given in your book. Properties of alkyl chain. So there what we have done. This is not in your syllabus. We have done the chlorination. In absence of sunlight, in absence of light, what happens? Alpha hydrogen is substituted by halogen. This I have done only for your entrance exam. Okay? And in presence of light, what happens? All the hydrogen atoms are substituted by halogen. This one I have done extra. I'm very sorry, sir. Some of one lady, she has complained that she cannot understand my handwriting. I cannot change my handwriting, dear. What to do? Okay, I'll try. Third, cleavage of carbon oxygen bonds. Okay. In this case, what did you find? In this case, we have done hydrolysis. And second we have done is the reaction with HI. Here what did you see? That in case of primary and secondary ethers, iodine atom goes to that alkyl group which has less number of carbon atoms. And what did you see the next one? Next one is that in case of tertiary ethers, in case of tertiary ethers, iodine atom goes to tertiary group. So up to this much you have done. Okay, I think it would be nice that if you write it, this is summary, then I'll go to the other properties. Please write down. Okay, it's easy for you to write. And if in between, if you do not understand, tell me, I will just read out. Please write. Yes, of course. Please write. Anything which you don't understand, tell me. After you finish writing, please tell me.
Done, sir.
Okay. So now we'll go for the last one, that is the electrophilic substitution on aromatic ethers. Electrophilic substitutions. On aromatic ethers. Okay, so I'll write here what example we are going to take. Anisole. Okay, now see here. See, this is anisole. See, oxygen is electron rich and it is being assisted by another electron donating group like alkyne. So they push the electron inside the aromatic ring. Okay. So what we will write now? Alkoxy. This group is called alkoxy. Okay. Alkoxy group is electron rich and it increases the density of electrons at ortho. Okay, these two are ortho. This is meta, and this is para. Density of electrons at ortho and para positions of phenyl ring by resonance. Let us see how does it increase. Now, so you know how to draw resonance structure. This. See, the lone pair of electron goes into the phenyl ring. See, this is the electron rich. Sorry, electron density of electron is increased. And whenever you draw electron, please move it from pi bond, not from C sigma bond. If you break sigma bond, the ring will itself will dismantle. Now see, it has come to the para position. Again, it has gone to ortho. Then from ortho, again it will go back to the oxygen. Okay. Okay, now it has come back. So let us write this hybrid structure. See, the flow of electron has taken place from oxygen and ultimately it has diffused into the main ring and it is increasing the density at 2 ortho position and 1 para position. And here we write this. Okay, so whatever we have said here, it is being proved. So please write it. Please write. Finish.
Yes, sir.
Okay. So now we'll go for examples of electrophilic substitution. Examples of electrophilic substitution reactions. Okay. So first we'll go for halogenation. Let us take chlorination. Okay. Now, in case of chlorination, see, in case of phenol, we did not use any catalyst. But for anisole or aromatic ethers, you have to use a Lewis acid catalyst. What does it prove? That hydroxide is a stronger electron donor group than that of alkoxides. Okay. So if you do the chlorination in presence of AlCl3 is a Lewis acid, so you will find is going to give you two products. OCH3, it is parachloroanisole and orthochloroanisole and parachloroanisole. But please remember, always the para product is more in amount. Why? Because when chlorine goes to a group like this, there is a problem of space is there. So we in chemistry we say steric hindrance. Stereo means space. Hindrance means obstruction. If the question comes why para product is more, you write because of steric hindrance, the ortho product is less. This is enough to get full marks. So we'll write now here major. Okay, and plus we'll write HCl. One of the chlorine will go and other chlorine will replace the hydrogen. This is for chlorination. If you do the bromination there, in this case you can also use the same Lewis acid. So plus bromine AlCl3 will get orthobromo anisole and you will get here para-bromoanisole. This is also will be major plus AgBr. Achha, now see, common name is orthochloroanisole. Parachloroanisole. What will be the IUPAC name? I have told you that ethers and halogens are considered as substitutions. So in that case, none of them are considered as functional group. So we have to number it on alphabetical order. This is methoxy, this is chlorine. Obviously, you have to put 1 here and 2 here. So it is 1 chloro, 2 methyl benzene. And this will be 1 chloro, 4 methoxy. Oh, sorry, methoxy. Sorry, dear. It will be 4 chloro, 1 chloro, 4 methoxy benzene. Okay? This is 1 chloro, 4 methoxy benzene. So this will be 1 bromo, 2 methoxy benzene. Okay, and this will be 1 bromo, 4 methoxy. This is IUPAC. Right. Done.
Yes, sir.
Okay, now we'll go for nitration. Okay. Nitration. See, whenever you carry out nitration for aromatic compounds, we always use nitrating mixture. Okay. So nitrating, what is nitrating mixture? It is a mixture of concentrated nitric acid and concentrated sulfuric acid. Okay. Concentrated nitric acid and concentrated sulfuric acid. So here, if I use nitration, so I'm going to use here a mixture of concentrated nitric acid and concentrated sulfuric acid, and I'll heat it. So here also you get a mixture of two products, ortho and para products. So you'll get here ortho nitro anisole. This is ortho nitro anisole, and what will be the IUPAC name? Please see here. This is methoxy and this is nitro. So in this case, alphabetically, this will come first and this will come second. So it will be 1 and it will be 2. So it will be 1 methoxy, 2 nitro benzene. Okay, plus you get here so this will be para nitro anisole. Why? Because the name is anisole only. Para nitro anisole. And what will the IUPAC name? It will be 1 methoxy 4 nitro benzene plus it will be H2O. Why? Because OH from nitric acid and H from benzene will go out. So here this also will be measure. Please write. Done.
Yes, sir.
Okay. Now we'll go for sulfonation. In your book, sulfonation is not given. In sulfonation, we take fuming nitric acid, means extremely concentrated nitric acid which contains dissolved sulfur trioxide. We heat it. Here also we get two products, OCH3, SO3H. See here, this is a functional group. So according to IPC rule, whatever may be the thing, if functional group is present, for numbering functional group is always preferred. And this functional group name is sulfonic acid. Sulfonic acid. All right, so this will be 1, this will be 2. Yes, if you go for classical name, this is orthomethoxy benzene sulfonic acid. Benzene sulfonic acid. And what will be the IPC name? Or 2-methoxy benzene sulfonic acid. Okay, plus you will get H2O. Again, you okay. And plus you will get the para isomer. It will be CH3 SO3H. Okay, let's get H2. All right. So what will be the name? Para methoxy benzene sulfonic acid, and or we 4-methoxy benzene sulfonic acid, and this will be major. After finishing, please tell me.
Sir, done.
Okay. Now we'll do Friedel-Crafts reaction. Okay. Friedel. Friedel. C-R-A-F-T. Friedel-Crafts reaction. In Friedel-Crafts reaction, what do? We take an aromatic compound and we react it with alkali chloride or acid chloride in presence of Lewis acid like aluminum chloride or boron trifluoride etherate, or sometimes we can use concentrated sulfuric acid, or we can use stannic chloride. Many other catalysts are there. Okay, so we'll classify them into two categories: alkylation and acylation. Okay, so I write now here alkylation. So in alkylation, what we'll do now? I write just opposite. CH3. See, one hydrogen is here and chlorine is there. It will go. Or if this molecule will come here, hydrogen from here and the chlorine from here will go. All right. In that case, AlCl3. So it will go to ortho O CH3. This. So what will be the common name? Orthomethyl anisole. Orthomethyl anisole. And what will be his IUPAC name? See now. This is methoxy and this is methyl. First four letters are same, METH in both the cases. Where does it differ? In methoxy, the fifth letter is oxygen, and in case of methyl, the fifth letter is Y. So alphabetically, this will come first. It will be 1 methoxy, 2 methyl benzene. 1 methoxy, 2 methyl benzene. Okay. So this will be plus HCl. This is 4 methyl anisole, or it will be 1 methoxy 4 methyl benzene. This will be all para products are major.
Excuse me, sir.
Yes.
That common name of the second one, it's paramethylacynol or 4, right, sir?
This
Not
is
4.
4-methyl. Oh, so yes, yes. Yeah, this girl is very good. It is paramethylanisol. Paramethylanisol, and IUPAC name is 1-methoxy 4-methylbenzene. Thank you. Done.
Yes, sir.
sir.
Right. Now we'll go for B. Acylation. In acylation, we will take acid chlorides. Okay. So this will be Cl, CO, CH3. This specific name is acetyl chloride, and its IUPAC name is ethanoyl chloride. So what you will get? See, H and Cl will go. So this carbon will be bonded to this carbon. So what should I do? I'll write it CO CH3. Now, dear, see that in class 11 you have already studied, but I know you successfully forgot. This molecule is called acetophenol. So what will be the name of this one? This is called orthomethyl acetophenol. All right. Now, IUPAC name I'll write later on. This is COCH3. As in previous case, please write below that paramethyl anisole. Below that you write measure. I forgot to write. Okay. This is called paramethoxy acetophenol. Okay. Okay. Finish. Then I'll explain. Then only I'll write down the IUPAC name. Finish writing.
No, sir. We're done.
Done. Okay, now see. This is called acetophenol. I'll tell you why such name is there when I'll go to the aldehyde ketone chapter. Okay? Huh? Remind me if I forget. Now, what will be the IUPAC name? See here. In this case, this is the alkyl group. So it is 1 and 2. Why you have to number this one? Because it is containing the functional group. So preference will be given to this. And this phenyl group is substituted on the alkyl group because it is containing the functional group. All right. And also, you know, when you number the carbon of the alkyl group, we always give preference to the carbon which is having the functional group. So because of that, I've written 1 and 2. Is it not the phenyl group is substituted on the first carbon of the alkyl chain? Okay, now see. I have told you in class 11 also, naming of organic compounds are not difficult. Only thing you have to follow, that is that secondary prefix means substitution. Primary prefix if the whole molecule is cyclic. So we will not consider this one. Then comes word root, means how many carbon the main chain has. Now comes what? Primary prefix. Primary prefix is ANE, ENE, and YNE. And what is that? Primary suffix. And what is the secondary suffix? Is the functional group. So this group is called phenyl. So I'll write here now phenyl, but I have to write the position where it is substituted on first carbon. So it's 1 phenyl. See, the whole molecule is not cyclic, so forget. How many carbon the main chain has? 2. So what is the word root? Sorry. ETH. ETH. Then, does it contain carbon compound double bond or triple bond? No. ANE. Then, what is the functional group? The functional group is ketone. This is ONE. When which carbon? First carbon. So we'll write now here ONE. So what will be the IUPAC name of this one? The IUPAC name of this one is 1-phenyl ethan 1-O. This is the IUPAC name of this one. All right. Now see. Let us go for this. For this one. See here. This is a substitution. And on substitution, you have another substitution. All right. That is, see, if you take your own body, how do you measure our height? We measure our height from heel up to the head. But we do not measure our height on the basis of the length from your heel up to the last end where your hair is there. In that case, all the ladies would have been taller than the gents. Huh? So we do not do like this. That is, your hand or your hair are part of your body, but this is not the main body. There we consider them as substitutions. All right. So here also, but okay, why I want to say. See, now, if you consider your hand is a substitution, but mind it, you are wearing rings also. Some of you are wearing bangles also. So your ring is not connected directly to your body, is being connected through your body through hands. Some of the girls are wearing ring also, ear ring. So if ear is the substitution on your body, then ear ring is the substitution on ear. So here also, this is the main substitution, and this methoxy group is substituted on the substitution. So in that case, we have to number it. But mind it, when we write 1, 2, 3, this means they are the carbon on the main chain. So we have to put this number within bracket. How do you write here initially? We have written 1 phenyl. Then ethan. See, why did I remove this? Yes. See, I have made a mistake. I did not tell you. This is a vowel, so this E has to be removed. This is a vowel, this E has to be removed. So E is not there. It's not there, I forgot to write. Okay? So it is 1 phenyl, ethan, 1 O. But this phenyl ring is containing a substitution. On what substitution? On which position? See, this is functional group attached to this, so I have to put here 1. Then this is 2. You know, dear, what I'll write now? I'll write a 1, then I'll put a bracket. Then I'll write here 1. Then I'll write here 2 methoxy, and I'll put this inside. So name is 1, 2-methoxyphenyl. Then this is the name of the whole thing. Then ethan 1. So similarly, below that also you write, see, it is in which position? 4, na? Below that also you write, that is 1, 4-methoxyphenyl. Ethan 1. Please remember. I know this type of names do not come in your entrance exam because they are too simple, but you should know. Okay, so I'll write here now 1, 4 methoxy. Most of the textbook they did not write the IUPAC name. 4-methoxyphenyl. Then I'll write ethan 1 O. Okay, so please write below the molecule. Okay, and this is major. So with this, I finish this chapter. Okay, I'll talk to you 5 more minutes so that we can have a recapitulation. Till now, how many videos you got from this chapter? 3 or 2? How many? See now, those who have registered now, he will give you a link. You can directly access there and you can see all the videos. All the videos you will be able to do. Because of that, I was telling you to register. So you need not wait for me to post it. This is advantage. And these videos will be available to you throughout the year. So before exam, if you have any doubt, you can even see those videos. So it is not that I created some problem. I wanted because most of the classes for other teachers, Rajdi, of course, you are posting videos, but in that case, you need not save them also. If you wish to save, is good, and if not, then you can directly access through the that side. So after you finish, you tell me. Finished?
Yes, sir.
Yes, sir.
Okay. See, now I'll go for a very small summary of the entire chapter. But before that, I like to tell you, I've already posted also in our WhatsApp group. See, in my class 11, I have given notes to almost all the chapters that I've given to you, and many of you have taken my copy and you have xeroxed it. But it's very incidentally, I yesterday I was looking the notes on S block and P block, my whole copy. I think maybe that someone has taken it and forgot to return me. Okay. So if by chance, suppose you forget, please check in your house. My own handwriting is not the Xerox one. All right. If you get, please notify me in that group. Otherwise, dear, I have to write the whole thing. It's very painful to write it. I made it very simple, and also for your entrance exam, I will written the note. Otherwise, to write one note for me, it takes around 60 to 70 hours. Okay. So please look into your bookshelf and you see, it's not that intentionally someone has kept it. Sometimes we also forget to return many things. Okay, please, my request, all of you check. All right. Now, in this chapter, we have discussed about alcohols, phenols, and ethers. Because why? Because in that case, what did you find? The functional group main functional group is OH. So if OH is bonded to the alkyl group, we call it alcohols. If it is bonded to the aromatic group, we call it phenols. And if the alcohols and phenols hydrogen is being removed, and if you put any alkyl or aryl group, we call them as ether. Because of that, the three of them are being placed in the same. Okay. So preparation of alcohols, we have already seen different methods by which the alcohols are being made. All right. And the properties we have found that alcohol shows various properties. I told you, never read chemistry blindly. Never try to by heart it. No, science is a subject of logic. If you spend little more time, you don't have to read it again and again. So alcohols we found that look at the molecule, try to find out the different types of bonds. And whichever bond is weak or polar, that bond will break and is going to show you the properties of that. So we have found in case of alcohols, oxygen-hydrogen bond is extremely polar, followed by carbon-oxygen bond. And also the carbon-hydrogen bond also may break. So if oxygen-hydrogen bond breaks, hydrogen goes out as H plus ion. There is any molecule which gives out H plus ion. It may not be as strong as our mineral acids. I told you mineral acids means all inorganic. But still it's going to show the properties of an acid. All right. But we found that alcohols are very weakly acidic. Why? Because oxygen is being bonded with alkyl electron donating groups, by which, due to repulsion, the dissociation of alcohol is very, very less. But still, if you react them with strong molecules, sorry, not strong, very reactive molecules, they will react. So we have found alcohols react with active metals, alcohols react with carboxylic acids. Alcohol not only forms esters with carboxylic acids, alcohol can form esters with different inorganic acids. Okay, alcohol reacts with Grignard reagent and gives you hydrocarbon. It's not in your book, but still you should know for your entrance exam. Then we have studied The property is due to the carbon-oxygen bond. Where carbon-oxygen bond breaks and OH group goes out as OH minus, that is, it shows one nucleophile replaces another nucleophile. So alcohol show the nucleophilic substitution reaction. Under the nucleophilic substitution reaction, what did you study? We have studied the reaction of alcohols with different types of halogen acids like HCl, HBr, and HI. And we have found as this reaction goes through carbocation intermediates, so more stable the carbocation is, faster will be the rate of reaction. And under this, we found tertiary alcohols reacts very fast, followed by secondary and primary. And on that basis, we have also found that we can distinguish primary, secondary, and tertiary alcohol by the reaction with concentrated hydrochloric acid and zinc chloride, which you call as Lucas test, and the Lucas reagent, anhydrous zinc chloride, and concentrated hydrochloric acid is called Lucas reagent, and the test is called Lucas test. For tertiary alcohols, immediate turbidity it gives momentarily. Then in case secondary alcohol, if you shake it after 5 minutes, you will find this turbidity appears. But in case of primary alcohols, you'll find it will never produce turbidity at room temperature. But that does not mean the primary alcohol does not react. Yes, primary alcohols do react, but at higher temperature. Okay, so we have seen the reaction with HCl. In case of HBr, we do not use anhydrous zinc chloride. We use concentrated sulfuric acid. And in case of hydrogen iodide, we use orthophosphoric acid because sulfuric acid oxidizes hydrogen iodide to iodine. This is an important question for your exam. Then we have read about the elimination reaction, beta elimination reaction or dehydration. If you heat alcohol at 443 Kelvin, in that case you find it gives you corresponding alkenes. But if the alcohols have more than one beta carbon bonded to beta hydrogen, then it can give you more than one alkenes. And which alkene will be more? The alkene which is more substituted will always form more in amount. It follows Sedgwick elimination rule. Then we have discussed about the oxidation of alcohols. We have found that alcohols can be under control oxidation, it gives us aldehyde, and if you go for complete oxidation, it gives us carboxylic acids. That is for primary alcohol. So primary alcohol, if you treat it with selective oxidizing agents like pyridinium chlorochromate, in short form we call it PCC, and this is also known as what reagent to forgot. Okay, I'll tell you later. Now, it gives you corresponding aldehydes. But if you react it with strong oxidizing agents, such as potassium dichromate in excess and potassium permanganate, whether in acidic or in alkaline medium, it gives us corresponding carboxylic acids. When you go to secondary alcohols are oxidation with weak or strong oxidizing agents under normal conditions, it gives us corresponding ketone. Ketones are not as sensitive as aldehydes to go further oxidation. In that case, you will find it will give you ketone. But if you do under boiling condition, then ketone molecules may break up to give you mixture of carboxylic acids. Tertiary alcohols are very, very insensitive towards oxidation because it does not have alpha hydrogen. But anyway, anything you do under rigorous condition or strong condition, then in that case, what it will give? It will give you corresponding ketones and carboxylic acids. All right. So reduction is not given in your book, but I told you if you reduce alcohols under with hydrogen iodide and red phosphorus at 423 Kelvin, it will give you corresponding alkanes. Then we go to phenols. Phenols also show the property like that of alcohol only. Phenol is acidic, but phenol is found to be more acidic than that of alcohols. Why? Because we found the resonance of in phenol does not bring stability due to charge separation energy. But that same thing is not prevalent in the phenoxyl ion. So phenoxyl ion is more resonance stabilized than phenol. Because of that, it undergoes dissociation. Clear? So phenol shows the acidic properties. So just like that, as we have studied in alcohols, here also we'll study the reaction of phenol with sodium, alkali metals. It reacts with alkalis. Alcohols do not react with alkalis, but phenols react with alkalis. But very interesting thing is that if you compare the acidity of phenol with carboxylic acids, in that case you find phenol is very weak. So phenols do not react with weak bases like sodium carbonate, sodium hydroxide, sodium bicarbonate or ammonia. But phenols can turn blue litmus red, which alcohols do not. All right. So we have studied the acidic property of phenol. You can see these videos also from there. You'll find. Then, if you go for the nucleophilic substitution reaction of OH group phenol, we find generally does not take place. Why? Because carbon-oxygen bond in phenol is having partial double bond character due to resonance. All right. So it cannot be broken. But under drastic condition, like if you distill phenol over zinc, in that case, phenols get reduced to corresponding aromatic hydrocarbon or benzene. This process is called dehydroxylation. Or one more example I have given you is this is not given in your textbook, is the reaction of phenol with ammonia. If you do in presence of catalyst and at high temperature, then in that case you will find phenols can be converted into aniline. All right, then we have gone for electrophilic substitution reaction. Hydroxyl group is a very strong electron donating group, so it increases the density of electron at ortho and para positions. So the electrophilic substitution reaction of phenol occurs there, and it can be done at milder conditions. So when you go for halogenation, suppose you come for bromination, in that case you find bromination of phenol with non-polar solvents like carbon disulfide or CCl4 gives us a mixture of orthobromophenol and parabromophenol. But if you do in polar medium like water, so bromination of phenol in water gives us 2,4,6 tribromophenol. Now, in case of nitration, is a unique thing. Phenol only reacts with nitric acid in absence of sulfuric acid. That too also in dilute condition to give you orthonitrophenol and paranitrophenol. How can you separate them? We separate orthonitrophenol from paranitrophenol by the process of steam distillation. Why? Because orthonitrophenol has intramolecular hydrogen bonding and exists in unimolecular form. Because of that, its melting point and boiling point is lower. So it comes out along with the vapor, water vapor. But it does not happen in case of paranitrophenol because it is hundreds and hundreds of molecules are bonded with each other through intermolecular hydrogen bonding. If you do the nitration of phenol with nitrating mixtures like concentrated sulfuric acid and nitric acid, in that case you get 2,4,6 trinitrophenol. It is so acidic, because of that its common name is picric acid. And picric acid is large volume of picric acid is being used for dyeing of silk and wool. Okay. Now we have gone for the sulfonation. If you carry out sulfonation at lower temperature, you get 2-hydroxybenzene sulfonic acid. If you do at higher temperature, 373 Kelvin, in that case, you will get 4-hydroxybenzene sulfonic acid. Phenols do not generally undergo Friedel-Crafts acylation or alkylation. The simple reason is that phenol is a Lewis base and catalyst AlCO3 is a Lewis acid. So they react within themselves before reacting with acid alkyl chloride or acyl chloride and form an addition product. This is important for your exam. All right. So now we have some special reactions also. These are extremely important for exam. Is the Reimann-Tiemann reaction. If you heat phenol in sodium hydroxide along with chloroform, and after that if you neutralize it, you'll find it gives us 2-hydroxybenzaldehyde. which is commonly known as salicylaldehyde. Is very, very important for exam. And why I given you another hint for entrance exam. Then instead of chloroform, if you have taken carbon tetrachloride, it gives us salicylic acid. Now another reaction is there, is called reaction, Colbase reaction. In that case, what you do? We heat alkaline solution of phenol in presence of carbon dioxide gas under pressure. Then and after the neutralization, we get salicylic acid. What is salicylic acid? Salicylic acid is 2-hydroxy-benzoic acid. Clear? And so these are the reactions of phenols. Now ether already we have done, is in your memory. Okay. Then again my request, please search out for my note, and if you maybe if you can locate with some of your friends, very good. Okay. Thank you, and I'm very sorry I could not meet you on Saturday because I had some personal work. I had to go out of the house. It was very urgent. So today at 8 o'clock we'll meet. If you have any questions, so we'll try to answer it. And again, my request is that please enroll yourself, okay, and send me the name to me, okay, and I will tell the group admin. Please try to find out that how many of you registered, and because every time I cannot remember. Clear? Thank you. Good day.
Thank you, sir.
Thank you, sir.
Welcome.